structure, and so for many years in this higher structure, there are many foundational work to build up the structures and things like this. But this work probably is it's like more like presenting an example into details, and it's a very, I guess it's a very classical example, like a classified space. Therefore, many people has worked on that. So, so if we didn't have the citation complete, please let us know. So first the result. So let's begin with the result. Finally, there's certain result. One can start a talk with a straightforward opening without too much technique. The first result is saying that we take the based loop group. It will become a Li Chu group on top of PEG. PEG is the path based at the identity E. And then it has 3 levels. The last level is a point. Well, you will see that's just a way to talk about Li Chu group. And then this Segal's symplectic form on this based loop group defined like this. It becomes a two-shifted symplectic structure, and I will explain what two-shifted means exactly afterwards. And here we require some conditions. G has to be connected, simply connected, and its Lie algebra has to be quadratic, namely with a pairing which is equivalent. And then there is a finite dimensional version of this story, which has been known for a long time. I guess it has been there. Well, we first actually saw this from a note of Allen. I think that was dedicated to Floor, and but maybe it's there. Oh yeah, and also in Brzezinski's book, there's some there's some hints over there too. And so we take the same sort of G and we form the nerve of G. Well, we know that's classified space is the geometric realization of nerve of G, and then we have this Cartan 3 form, and then this 2 form. Well, in Allen's note, he dedicated to, I think he said it's from Yao Kashan's master thesis. And then these form together, they also form a two-shifted symplectic form. I think we say that we see the claiming, for example, in Safonov's paper, and maybe also in other papers over here. I think also in Lee Bland and Chavera, and they have this. Yes, that's right. That's another thing. Yeah, I forgot to say that. In Asper's note, there was Schumann's calculation. If we do a homework well, up to some exact forms, we didn't really verify. These guys also show up. And then there are certain, well, let me mention, there's then these 2 models, and there are these, I think there's another result of Eckhart and Marco. They also studied the relation, I didn't write over here, relation between this omega and Segal's omega, and they were related by a certain Dirac structure. And over here is some sort of our relation is from another point of view. So it turns out that this evaluation map simply this guy evaluate at the end point, and the other evaluate, you need to evaluate at 2 points. I will explain which 2 points, and then you can extend it to a simplicial map. And this guy will provide you a Morita equivalence. And then between these two groups, well, actually this one is just a one group. And then when you pull back these forms, they are the same, they stay in the same class. Well, we can actually, it took us a long time to figure out the exact formula of this form over there. It's also one of the work that we worked a lot with like an explicit formula. And then the next one, right. So it turns out there is also.
Sorry, Chenchang.
Yeah, sure.
But I don't know whether we are supposed to understand the details, but this capital D, what is this capital?
Oh, yeah, thank you very much. So this capital D, I will explain later. Capital D is the run D plus minus this the simplicial D. It will appear later.
Okay, thank you.
Thank you. And so then, well, then for people who are like my colleague Malay, and Kiro, people who favor in double structures, Henrika. So there is also a picture in double groupoid. So this omega and PG, they form a double groupoid. And then they also evaluate to this very simple double groupoid, and all these forms find their places too. And right, and then again, when you pull back this form and the other form, you come over here. You need to make another eta together with the Segal's omega. To make it work, and then again it's and they stay in the same class over here. Then D will become I guess plus minus D plus there you have two simplicial direction, delta H and delta V. And we also found this explicit formula out. That took us also a long time, but it's nice formula. It's very explicit. So that's the example I want to explain over here. And well, I have to say it's a work in progress with me, guy. We were still calculating different formulas even this morning. So and okay, so let's start. Maybe I start with this to explain this Li2 group first. And especially if I want to say clearly what is two-shifted symplectic, I will really need the foundation. So a Li-n groupoid is a simplicial manifold, satisfies certain Kant conditions, and over here it's an n. Therefore, this Kant condition is Kant condition from X the mth level to the Horn space is a surjective submersion for everything, and is an isomorphism for m greater or equal to m plus 1. And this Horn space, let me explain a little bit. This Horn space, this notation mj denoted mj horns in X, that means that well, maybe it's just easy to draw a picture. So for example, 0, 2, 0 horn, you sort of remove the simplest inside, and also the 0 face, and 2, 1 horn is like this. So it's some sort of fiber product. For example, the two one horn, you have one x1 some side and another x1, and you need to match them at x0 over here. So some sort of fiber product. And as long as we are differential geometry, we know that it's sort of dangerous to do fiber product, right? It might not be a manifold anymore, but what is really nice, I think that's Andre who proved it, is that inductively you can show that with lower Kahn condition, which is naturally true when m equal to 1, it's always okay, because when those zero horns, they are just upsilon, they're just points, and they're naturally just manifold, and you can inductively show that these horn spaces are going to be manifold naturally, so you don't have any worries. And for two group point, what we care is about two group, right? So then Lie two group is something that you have to have x0, it's just a point. You have to have x0. It's simply a point. And why is something like a Lie two group, right? So there are many people who are much more familiar with the version of Lie two group via categorification, namely a Lie group point, a group object in the world of Lie group point, right? So how do I see this? So over here I've got x2, 3 arrow to x1, and going to a point. And here is my space of triangles, and here is my space of one simplices. And then I'm going to take the bygone in x2, so things like degenerate triangle. I think I make this side very short, so then it will become a groupoid over x1, and this whole groupoid carry a group structure. Group in the word of groupoid, Lie groupoids. So that's how it goes. And so that's our. We'll see this example later much clearly. And now when we have a n groupoid, Lie n groupoid, then we can form we can form this tangent complex. We take a point in x0, then this point, because x0 sit naturally also in x1 via identity, in x2 via identity, and so on. So this x can be viewed as a point also in x1, x2, and so on. Then we take the tangent space at x of this simplicial object, x over here. Then we have a simplicial tower, but now it's a simplicial vector space. It's not just a simplicial manifold, because each one is a vector space. Then we can form its normalized complex. And it turns out this normalized complex is simply the kernel of this horn projection of the last horn. So in this case, 0 is this horn, the last horn over here. So this normalized complex is exactly the kernel of the horn projection. And then one form it's a complex, we need the differential, right? The differential, we use the last phase map. And then we don't we can define then the complex of vector bundle by taking the kernel of this last Horn. I'm sorry, the last Horn projection and restrict on X0. So it will be a complex of vector bundles over X0. The differential is still this last phase map. That will give us this complex of vector bundle. That's the that is the tangent complex of X. And what I did over here is some sort of Dalton construction, right? So there is some other way to realize this normalized complex. Namely, you can take the quotient, and then this. Sometimes people also see this this tangent bundle, this vector bundle in this form. I think I also find in Ezra's notes in the quotient form. And then if you have a Lie n groupoid, because you see this this Horn projection, after a while it become a after a while it become a isomorphism. Therefore, this tangent complex will just become trivial after a while. And so that's our tangent complex where we're going to, it's going to be important for us to see whether the symplectic form is degenerate or not, right? Because we sort of wish, okay. So then the next concept we need is to talk about this symplectic form. Let's begin with a differential form on a Lie n groupoid. And we take this double complex, right? So that's this delta and D that we were talking about before. So this double complex in on one direction is the simplicial direction, like here. The other direction is the Derived direction, like this. And we call this differential form normalized if it is zero on degeneracies. And we call it closed, and if it is d of omega is 0 with respect to the total differential d. One direction is Derived, the other direction is simplicial, right? So this little delta, this simplicial delta. The simplicial delta is some sort of, well, depends on your favorite sign, some sort of defined by pullback of these phase maps. And then we can talk about what are M-shifted K-forms. So this omega as a differential form usually has many components, right? So for example, this omega can have components here, this one component omega 2, and you also have omega 1, and you also have certain omega 0. So usually to have a total degree 4, you can have like many components. And a M-shifted K form has total degree M plus K. and it consists of a k form on xm and a k plus 1 form on xm minus 1 until the end. And we call such m-shifted k form pre-symplectic, well, if it's closed, right? And normalized, and we need it to be a true form. So in this way, we call it m-shifted true form pre-symplectic if it's normalized and closed in this way. And then now to define non-degeneracy, well, I actually didn't find. So somehow this the most convenient measurement I found is again in Ezra's notes, and somehow I didn't find such we didn't find such convenient way for at least for differential geometers in other literature in algebraic geometry, and so but I guess it's also known for a Poisson community in the name of IM forms, so infinitesimal multiplicative forms. It's so you see, I take a tangent vector on degree L, and I take a tangent vector on degree n minus L for a m-shifted pre-symplectic form. So it's a true form, right? That can define. This is some sort of it's like you differentiate, use some sort of von Est. You get some something on infinitesimal on the tangent complex, right? And the way you do it is through this formula. You take certain shuffles and you embed V back to the level M via different degeneracies. You embed again W to XM via different degeneracies. And when I think when M is one, it is exactly these IM, well, at least a part of the IM forms that's appear, I think, a lot in appear a lot in Henrique's work, Marius and Henrique's work, which was initially funded with in well, I guess article we rewrote even when I was a PhD at Berkeley with Alan, Henrique, and Marius. So this then you can verify, yeah. So then you can verify this form is bilinear and graded antisymmetric, and it satisfies this condition. And you can actually verify much more, but these two are the other two which is important for us. So once we have this condition, then we can see that it does not. This guy does not only live on the tangent complex, but it also descends to the homology, and it's important for this BG example to verify Segal's form is non-degenerate, to descend to the homology. And so omega is non-degenerate if this IM form is non-degenerate on this homology. So in algebraic geometry, they often say the omega induce a quasi-isomorphism between tangent and cotangent complex. And this is really a very, very explicit way to verify this. And in this case, we call it a n-shifted symplectic form on this Lie n group, right? So this n and m can be different, and it does not have to be 2. And now, yeah, so now let's go to this BG example. And we take, so let's arrive this Lie 2 group, right? We take a Lie algebra, and we take the integration infinity group that is defined. So on each level is defined to be the space of Lie algebraic morphism from the tangent complex tangent of a simplex to the Lie algebra G, and then we do a 2 truncation. That's how we arrive at this Lie 2 group. Of course, over here it's and G is the connected, simply connected Lie group of little g. And let's have a look. So what is this structure over here? PEG is the set of, as I said, it's the space of paths which start at identity. And omega g is base loop. Let's give 3 points on this loop on 0, 1, 2, and we put 2 at point E. And then these 3 degeneracy over here is D0. So over here is D0. D0 of this, let's say this is a loop tau, is tau 0. Tau 0 travel from 2 to 1, right? So, and tau D1 of tau, I travel from, so it's also identity, 2 is identity, 2 to 0 the other way. And D2 of tau, I want to take this guy, right? But it does not start at identity, so I have to move it. I have to move this guy back to 2. So I move. So basically it's, I think it's, if you really write down in formula, it's, have to move it. You shift it by this point to identity. You have, and you can also similarly make, you can verify it will satisfy Kahn condition. What does Kahn condition mean? It means that I have a horn. So here I have a horn things, I have 2 such paths, then I can feel this horn, right? I can feel it. Oh, wow, I have 2 such horns. I can all the time connect these 2 ends because my G is is connected, and I connect it in only one way because it's simply connected. Well, and then the tangent complex is of this guy is loops in little g based at 0, and path in little g based at 0, and this partial map over here is simply the inclusion, and afterwards it's all 0. And then on this, so why we think this omega g should take a 2 group structure is also because in the end it comes from this Chern-Simons. Chern-Simons, it's a phase space of Chern-Simons sigma model where you can see the connection, a flat connection on 2-dimensional space, right? So in the end, it should really be a true group, because over here, this flat connection on D is, see, it's these guys. It's the algebra. It's the second part, and the gauge exactly come from the third level of this integration, and then, well, I guess, and then this can be also realized as a symplectic reduction we saw in Marin-Wood, and then you obtain this Segal's symplectic form, and it's symplectic, but we need to say it's like a symplectic in a new way, right? So we need to verify several things. Here, first, it's normalized. Well, you can verify it's normalized, then it's multiplicative. Once it's
Chenchang,
yeah.
Could you say like it's multiplicative? How does one check it? But probably I'm still somewhat missing how those definitions work. So this delta omega equal to 0. What does it mean, this equation?
Right, exactly. So very good question, and because once you need to verify it's multiplicative, you need to go to the mysterious the third level. The third level, that's the third level. Third level is a tetrahedra. Thank you to ask this this question. So it's you've got like 3 loops. You put them together, right? That's your third level. Let's write more or less like a 3, but it's not really 3 because it's a fiber product. Between these 2 loops, you need these to glue them together. And then you will have like 4 phase maps, D0, and which face this tetrahedra in 4 phases, right? And then you need to verify that D0 omega minus D1 omega plus D2 omega minus D3 omega equal to 0 on this new fiber product.
And a naive question, is it 0 because every edge is an edge of 2 triangles and they cancel, or there is...
It's more or less like this. It's more or less like this. That's how the calculation goes, but one needs to be, one needs to be careful. Why one needs to be careful? Namely, it does not work for any omega. It works for this omega because the end this omega in the end you can use Stokes. There's one step you need to use Stokes. It's more like this, more or less like this, except for the endpoints. You have to be careful because of this guy, because of this shift.
Okay, thank you.
Because of this shifts. So you if you and fortunately you go inside it and the shift work. You will see that here it's lucky. All the shift work out. In the double picture, the shift doesn't work out. That's why you've got in the square picture the shift doesn't work. Oops, the shift doesn't work out. That's why you've got like extra 8 over here. But in the triangle picture, the shift just work out very nicely. So this Segal's form is inadditional multiplicative, and therefore is closed. It normalized closed, so it's at least the pre-symplectic to shift it, but then let's verify it is non-degenerate. It is non-degenerate. We do a calculation of this IM form, infinitesimal form, and then we found it out that it's pairing at the endpoint. So you see, it's not non-degenerate on the nose. You have to go to the homology because you have to do, and this guy is exactly G, and this projection is evaluate at point evaluate 1. Therefore, evaluate 1, this guy is non-degenerate in gen, but just live over here is not. So it's a two-shifted symplectic form that we verified. That's our first result. And then well, it's just a comment that in Andre's paper, in Andre's work, he verified if you use this omega to do a prequantization, you end up with a what is this loop space, central extension of loop space, and then this guy provide a model for string G. So in this case, in this sense, you can also view the string G as a prequantization of this two-shifted symplectic form. And then let's have a look at the finite dimensional model. Let's recall in the finite dimensional model, it's two-shifted symplectic, and that's verified by before. And okay, so let's try to build up the relation between them. I have this infinite dimensional model, and I have this finite dimensional model. And one very easy map between them is evaluation, right? So on this level, I evaluate like this, at the endpoint, and then I also evaluate a loop. If I have a loop, I evaluate also. Well, I evaluate at the endpoint of this guy, 0 and 1. So the other 2 points, which is not identity. Right? So I guess this point is red, and this point is green. And then one can extend this evaluation map also to higher levels. Well, on this tetrahedron, you also have a way to evaluate to 3 copies of G and so on. Well, actually, you only have to do once over here. Then for the rest is automatically you generate, because this is cosecant to cosecant, and then the calculation comes when we try to pull back this these 3 form, Cartan 3 form, and Karshon-Weinstein 2 form. You see that's how where they live. They also live over here. They also live on degree 2. Well, they're also two-shifted symplectic, right? They also live over here. And what's the difference between them, right? Are they actually related? And it turns out that they stay in the same cohomology class, and they differ by a exact form, which take this which take this formula. It took us a long time to get this form, though. We tried different transgressions and didn't work out. And but this one, the simple one, just one, and works out really fine. And then you can also verify that this evaluation map is very nice. It doesn't change the form, more or less. It also doesn't change the group height. So introduce actually Morita equivalence between these Lie two groups. Over here, let me just mention there are also Morita equivalence between higher Lie groups that one can use. So it's actually not so hard. When you have two Lie n groups and you have a map between them, you call it as a hypercover if this natural projection from X2, so this is a boundary of the of this simplicial manifold. That's a boundary of the simplicial manifold. If this guy is a surjetic submersion, and when it's bigger or equal to n, it's isomorphism. It's just this. I think it's called Morita morphism for Lie one group, right? By certain people, and Morita equivalence is some sort of zigzag of these hypercovers. And there are many people studied this. I give the reference over here, and then you can verify this evaluation map. It's you don't have to go through a zigzag. You don't even have to go through a zigzag. Right, it's Banach manifold, right? Right. So that, Marco, you're right. There's some details over here. We cannot have smooth map to have manifold. A Banach manifold, you need the home space to have CR. So with a finite dimensional R. Where is it? So these loops are not smooth loops, but up to I just right. And that's a typical trick people use, right? Up to people sometimes say CR plus 1, and right, and where are we? So yeah, right. So these are. Then once we are in Banach manifold, then then submersion makes sense, right? Make perfect sense, just like in for finite dimensional manifold. And then this evaluation map gives you one of those hypercovers. So basically, these two models, finite dimensional model and infinite dimensional model, they are like pretty much same now, not just form, and also the group itself, the group itself, and therefore they're all some sort of presentation of the class infinite space BG, right? Okay, different way to understand BG. Then there's another argument. We can do a von Est differentiation of this from forms on NG. Okay, so this forms on NG to forms to the infinite dimensional picture. And the infinite dimensional picture is this well algebra. And over here, you can really view it as some sort of forms on the DG manifold, right? And which is the tangent complex of that guy. And then if you perform this von Est, you will obtain, after sign, the pairing you had on G. So really you can view this as an integration of this quadratic Lie algebra. And you can also say this is the IM form of this shifted symplectic, right? And but for the higher picture, it's so the higher IM form is not not yet completely figured out. I hope people it's nice subject. People can and there is explicit formula over here already. People can invest a bit more. And okay, so let's go to the double picture for the rest of the time. Actually, this Lie-2 group is really nice. It's actually a strict Lie-2 group. In the sense that if I just take bygones in omega g, it is still omega g, because if you take a loop and if you take a bygone, it's still a loop. Okay, and this omega g going to PG is a Lie group wide, right? So it's the picture is like this. 0, 1, 0, 1, and well, let's yeah, the direction goes that. Then this is the identity, the path start at identity, right? So that's how the group wide is, right? So it's some sort of homotopy group wide, right? So that's a arrow inside. The path is in this base loop is a form a group wide over this base path, and then it's a group. It has a group structure, right? So you just use the pointwise multiplication that will give you a group structure, and that's translation of this Lie-2 group to, well, this sometimes people also call it stacky Lie group or Lie-2 group in the categorified sense. And then or the sense is a double Lie group wide for people who are familiar with this language. And then this Segal's omega sit over here again. In the picture, I sit over here. So you see, this is a double picture. Now you do not only have so this simplicial, you have two directions. You have horizontal simplicial and the vertical simplicial. And of course, d omega is already still 0. Like the horizontal ones are 0. Like that calculation is like we done before. But the vertical one is not 0. And therefore, very by so by certain this is a transgression of Allen's capital omega, and then this little alpha, I think we saw the first in you put a 8 over here, then a row of omega of Segal's omega that will make this double picture nice. This guy, or if you want, you can call it quadratic anymore. But anyway, it's a 1-1 shift to 4. And this evaluation map, right? So we evaluate omega. That's just
Chenchang, I think you're muted.
Yeah, at least I no longer hear anything.
Now it's better?
Yes, I think your connection.
Now I hear you.
Okay.
Yes,
So
I think your
again, we
connection
want
is a little
to,
unstable.
can people?
Oops. Yeah, there are some. For me, there are some breaks in the sound. Now to hear you again, Chenchang.
The door, maybe that will make the internet flow better. I don't know.
Mm-hmm.
Let's try.
But maybe also switch off your
Psychologically, it works better.
Maybe also try to switch off your video, not the one that you're translating to us, but
How about this?
Yeah.
I switch out the video.
Yeah, okay, yeah. Yeah, now go ahead. Oops. Oh, yeah. Yeah, Chenchang, unfortunately, at least I don't hear anything. Sorry about that. Nikita, what do you think?
Oh yeah. So let me do this.
Okay.
Yeah.
Okay. So is it better now?
Maybe.
Oh. So I kept only one of them.
Okay.
So I can also move to a place with better internet, because I just have a pad now. And where are we? Right. So we will again have all these
So
forms.
now you have to share your screen again.
Oh, all right. So let me share my screen. Okay. Can you see
Yes.
it?
Yes.
Okay, great. But we're at the very end now, so it's also good. So we have this again, this evaluation of these forms, and then magically it still works out. So you put this guy back, this thing back, and you compare with this infinite dimensional picture, and naturally we still find they just differ by a exact form, and we can even find the explicit formula inside. I mean, well, it's not totally. Let's say there's certain luck inside, but it's also in the end it's also because of this, right? Because there's just one generator, but of course when we are in differential geometry, we have R. Then we have to be careful that this form when you pull it back, it does not differ with some sort of multiple, and therefore it's also lucky that we can actually find these exact forms over there. So over here, the exact form is made up by this alpha, this transgression of Cartan 3 form, and transgression of this 2 form. And so my time is almost up. Let me just make comments in the end. So we did all these different, like a zoo of symplectic form is actually also to answer well, try to answer some sort of mysterious thing in my heart for a long time, right? Because there were some effort to integrate Crude algebra, right? And they come out. There are many symplectic form comes out. They're all different, and then we did in this simplified version, right? So this G shift by 1 is very, very special. It's Crude algebra over a point. And even in this case, we see like a different symplectic form comes out, and they all differ. But then, at least in this case, we're satisfied. Even though they're all different, they stay in the same class, and we can find out the difference between them. And for example, one of them, I think Raj and Shang, they use this double picture to integrate Courant. It's more or less like this picture I just mentioned. And they did a Artin-Mazu codiagonal and transformed the double simplex picture to a symplectic picture. We can also do it here. When we do this Artin-Mazu to this double, it will just end up with no surprise. It still end up with this Li-Chu group we had before. But this form, this symplectic form, will become a different two-shift form. That's why, like, you use a different way to integrate it. You always use you cannot promise to end up with the same form, but hopefully they stay in the same class. Well, to find out whether this form stay in the same class differ by another sort of exact form is still under calculation. So as I said, it's a work in progress. So thank you very much. I finished my talk over here.
Thank you, Chenchang. Please, questions or comments? Yeah, Marco.
Hi, thanks for your talk. I was just wondering, at the end, are you basically saying that depending on how you present this this stack, like depending on how you present it as a simplicial manifold or as a bisimplicial manifold in the finite or infinite dimensional setting, you get natural symplectic forms, but they don't exactly agree? You're saying that that it demonstrates the fact that it's really just the class of the closed form that is important?
Maybe, yeah. So the natural form arrives, they don't naturally agree, but the class, as we calculate until now, they all agree. And it could differ by a constant, right? But they just agree.
The reason that I ask is just because they, you know, the way they define a shifted symplectic form is that it should be it should be an element in the it should be a cocycle in the complex of closed forms, right? So it's, when you represent it in one of your models, it makes sense that that it's not exactly the cocycle itself, which is the symplectic structure, but rather its class in the closed forms. So maybe that is what you're kind of explicitly demonstrating.
Say it again. So this, you mean
like in the literature about shifted symplectic, right? The way they define it is that it should be a closed form, but it has a class in the complex of closed two forms.
Es de posición. Sí.
It's all right. Maybe we should discuss it another time. Okay.
Sure. Yeah. So I haven't figured out whether that's the same class or not in this fine resolution. Yeah, we can talk about later. Yeah. Thank you very much.
More questions or comments?
Could I ask, this Artin-Mazu codiagonal rarely preserves the Cartan condition. So do you have a
No, it does not all the time preserve condition.
Right. So do you have a situation here where it does produce a lead?
Does or does not? Say it again.
Do you, in your case, does it produce something with satisfying the Kahn condition?
Yeah. In my,
so
in this
why is that? Why does it happen to produce a solution of the Kahn conditions in this case? That's my question.
Why? Oh, I don't know. It's we just calculated. It's this thing.
I see.
Yeah.
So you don't have a sort of background reason, a more general, because I'd be very interested to know if there's some sort of more general principle that leads to the Artin-Maser construction having Kahn condition.
Preserved, right? Yeah.
I mean, if you know any, I'm happy to hear. Yeah. Okay.
Oh, definitely. Thank you. Yeah, I need to think about why what's the reason in this case, but in this case, why are you interested in this?
Well, who isn't? I mean, functions the vibrancy are very important. Yeah. I think it would be like it. I don't know. I mean, I always forget is it right adjoints or left adjoints in the Quillen pairs between closed model categories that are meant to preserve vibrancy. But anyway, preserving vibrancy is an important condition.
Yeah. So it's not just our thing end up to be a lead to, and also in their Courant, in the calculation Courant, so they did for this guy. They also happen to be a lead to.
Yeah.
But in general, there are counterexamples.
Did you say that this was a strict, the thing which is near the bottom of your page? Did you say it was a strict lead to groupoid?
Yeah. It's a strictly to group. This guy's strict.
A strictly to group. Yeah.
Yeah, it does not have associator.
Right. And you said it's 3 co-skeletal as a simplicial manifold.
Right.
Okay.
So yeah. Thank you for correcting me.
And it's an Artin-Maser codiagonal.
Yeah, and it's an Artin-Maser codiagonal.
Why do you call it codiagonal? I would call it diagonal, but anyway.
Well, the reference book is quoting this. I found it from Tim's book. So it's
all right.
Yeah.
Okay.
So,
because in the homotopy literature, it's usually often called a diagonal. Okay.
Okay.
Yeah. The reason I'm saying that is because if you apply it to a bisimplicial abelian group, then it actually is it's the simplicial object that corresponds to the totalization of the double complex. So it's the lift to the simplicial world of taking the tot of a double complex and forming that corresponding complex. So it's a very natural construction. Yeah.
Okay.
All right, thank you. Eckhart and then Simon. Eckhart, did you want to ask a question?
Can you hear me?
Yeah.
Okay, microphone was turned off. Yeah, you're looking at this simplicial space extending PEG, the base path space, and comparing it to the simplicial space BG. So I'm wondering, according to my experience, the unbased path space, or say space of quasi-periodic paths, also has very nice properties. And on the other hand, EG, well, the formulas for EG are often easier than the formulas for BG. So I'm wondering if there's some extension of the story to, say, the full path space.
I understand you. So you here we replace it by PG, just the full space, right?
Yeah, or maybe quasi-periodic paths, yeah.
And even quasi-periodic path. but quasi-periodic path is a way to extend loops, no? So it says that it does not have to come back to itself, but it's just quasi-periodic. And that's what I understood. So and okay. So anyway, so a path and or quasi-periodic, and here maybe the entire loop or something like this. Oh. Yeah, we haven't thought about this, right? So this construct, why to, yeah. We have not yet thought about this. Thank you, but that would be nice. That's right, because because yeah, it is this guy which has a nice representation theory, right? Yeah, we need to explore a little bit, right? Thank you. And because right, thank you for the suggestion. We need to think a little bit more, right?
Okay, thanks. Dima?
Hi, yes, I can unmute myself. It's about your remark on the string to group. So you seem to have interpreted the construction of Bias, Kranz, Schreiber, and Stevenson as first constructing a hypercover. So this one, this omega into P
here, yes,
that one, constructing a hypercover of the nerve of G, and
I didn't hear hypercover of what?
Of the nerve of G.
Yeah.
And then building the central extension, well, the principal shifted circle bundle over that.
Right.
And Chris Schomer-Fries constructed a finite dimensional model of the string G.
Right.
By also constructing a hypercover of the nerve of G and then building a central extension of that. Except that his hypercover was finite dimensional, and it used this cover, like in the usual sense, of the group G. I think it's the one that Eckhart had constructed earlier.
Right. So he divides this G into many parts, open sets.
Yes.
Right. Open set, and that was the open set that Eckhart constructed before, right? Then pull it back, right?
Right.
Exactly.
Well, my question then is, well, have you thought of constructing, of building up this shifted symplectic structure on that hypercover instead of this infinite dimensional one?
Right over here. You see, may I ask you a question? So the gain of this infinite dimensional structure is that we have like a really natural two form over there, right?
Yes.
And if I just have the finite dimensional hypercover like this, and maybe I guess over here is some sort of but then what would be the true form? I guess the true form. You're right. We don't know what the true form is, but maybe we can move this the Segal's true form to here in a certain way, right? Because you're right. So because these guys, they actually sit inside. Maybe one can pull back this Segal's form on this finite dimensional guy and find out some other two forms. Maybe it's already, yeah. Maybe we'll find out that that's actually already another known two form. I wouldn't know now what that is.
Right. Yeah. I mean,
what could it be?
That's well, as just said, I have no idea, but
yes,
yes,
definitely we should put it back. Yeah, you're right. Yeah, we haven't thought about. Thank you. We'll put it back and have a look what that is. Thank you.
Okay, thank you. Any more questions or comments? Maybe I have just one, perhaps somewhat technical question. So you have this mysterious one form eta. Could you say a couple of words about it? For instance, I got a bit lost, and it's a one form on what?
Oh yeah.
Eta.
So it's right. This is a one form on the next level already. Like so you go here. What you do is it's a nerve of omega g, right? So eta lives here. Eta is a one form live over here. And how do you get this one form? You see, I have omega. I have this omega live on g times g, right? Then I do a transgression.
But do we have an explicit formula for it, or it's only in principle defined?
Oh, we have an explicit formula. So we do a transgression of Allen's true form, and we do a d delta h, or what is that? So some sort of d0 pullback, d1 minus d1 pullback of it, and then we do a delta v of alpha. This alpha is a difference between Segal's true form and the transgression of Cartan's free form.
Okay.
So there's like a very explicit formula. It's just a bit long.
Okay. Thanks a lot.
Thank you. Thank you.
So if there are no other questions or comments, yeah, let's thank Chenchang again. Thank you everybody for participating, and next week we'll have David Martinez-Torres speaking on global Poisson. Well, thank you and see you soon.
Thank you.
Bye-bye.
See you soon. Just for the committee member, we go to the other room. We go to the other Zoom room to talk about the committee issue. I inform